So we're going to be talking about images. Specifically, we're going to talk about spherical mirrors, which are mirrors that are in the shape of a small section of the surface of a sphere, which just basically means that it's circular like a sphere. So they can either be concave or convex. Today we're going to talk about concave mirrors for the most part. We're going to do a problem that lets us take a look at how images are formed from that concave mirror. So to start off, the problem reads, object O stands on the central axis of a spherical mirror. The table gives the object distance, type of mirror, and focal distance. Find the image distance I and lateral magnification M of the object, including signs. Okay, so I'm going to write out this table really quick. We have P to represent our object, which is at a positive 27. The mirror type is concave, which I'm going to abbreviate CC. The focal distance, F, is 43 centimeters, but we do not know the sign of this currently. I, the image distance, we do not know, but it will also be in centimeters, and we want to find the magnification. So, to begin, we will look at the relationship between all of these, which can be seen in the mirror equation. The mirror equation is 1 over the object distance plus 1 over the image distance equals 1 over the focal distance, which is also equal to 2 over the radius of curvature. And the radius of curvature is just the point. You'll be able to see it better when we do the ray diagram after this, but it's just the point where the circle that would be where the sphere is for that mirror, if it was complete, is the center, and the radius would reach from that point to the center of the mirror. So going from this, we know that because it's a concave mirror, the sign for our focal point will focal distance point thing will actually be positive, because only in convex mirrors do we have a negative focal distance. So with that information, we can go ahead and put in 1 over 27, that's a positive 27, plus 1 over I equals 1 over positive 43. And with a little algebra magic, we find that that is equal to, well, I is equal to sorry guys, my pen froze for a second. I is going to be equal to negative 72.6. I apologize for my handwriting, guys, too. I don't exactly have the best technology for this. Anyway, so that will be negative 72.6 centimeters. That is our image distance. And then we want to calculate the magnification. So the equation for magnification, one of them, which isn't necessarily relevant right this second, but I'll tell you anyway, is the absolute value of magnification is equal to h prime. Ugh, why did it do that? H prime. Stop. Whatever. Alright. It's being dumb. Well, imagine there's a prime. Well, I'll just put I, because it means image, and this is object. So anyway, the absolute value of the magnification is the image height over the object height. That wasn't given to us in this particular problem, but had they given it to us, we could have found the magnification that way. However, in this problem, we're going to have to use m equals image, it's negative, I believe, over distance of object. So our image distance, we said, was a negative 72.6, and then our object distance was given to us and was 27. It was positive. But we're going to put a negative in front of all of this, which 2 negatives and a positive is going to be positive overall. And again, with some algebra, that gives us a magnification of 2.7. Now this magnification value is useful, say, if we had either this image height or object height. We could use it, like if we had the object, we could multiply it by the magnification to find the image height and vice versa. So, because we don't have that, we won't worry about it. But I think the best thing to do now is probably explain a couple things about whether the image that we found is real or virtual, upright or inverted, and on the same side or the opposite side of the mirror. I think the best way to see this is probably to draw it out in an array diagram. So let me get some stuff situated really quick. Get an axis drawn. Actually, it may be better to have the y-axis not drawn like that, so that you can see the mirror itself better. Let me just start that over entirely. Okay, so, did it again. Let's just have the horizontal axis really crooked. And then we'll do blue for our mirror. It's about as good as that's going to get. Pretend that's in the center. So that's going to be our concave mirror, and then we will have our focal point, they said, was at, was at a positive 43 because it is a concave mirror, which means that it's going to be in front of the mirror, making it positive, which is technically in the negative x direction if you think about like a quadrant, like a coordinate plane, but anyway, it's backwards of that. So we have that at this is our focal point at positive 43, and then somewhere out here we would have our radius of curvature. This is not necessarily to scale, obviously. That's an R. And then we would have our object. Well, let's leave it in green, I guess. No, let's do black. Okay. Our object's going to be, say, here. And that's P. And it's at a positive 27. So actually, I did that in the wrong place. I apologize, guys. It would actually be in front of this focal point. So it would be somewhere in this area. Probably, this is again not to scale or anything fancy, so there's that, and that's going to be our object. And then The easiest way to approach a ray diagram is to keep in mind that the easiest two rays to draw are the one that's directly, this is supposed to be parallel to the axis here. And then as soon as it hits the mirror there, it's going to go through the focal point, which in this case is in front of the mirror, so it'll come back this way. That should ideally go through that red dot there on the axis. And that's one of your rays. And then our second ray, you can take and go directly from the focal point. After you draw that line, we can kind of start with the second line that is kind of like an imaginary little dotted line to begin with, and then that line continues till it hits the mirror. This is supposed to be more straight here, but dotted sort of, because it's not the actual ray. The only part of the actual ray is this portion. So then that ray continues. After it hits the mirror, it will go parallel to the axis. And if you continue these, you can tell where the image is on the opposite side of the mirror, because this line here continues. This is awful lines, I'm so sorry. And so does this one. So then our image would be here, at this point where those two lines intersect. Again, I apologize for this drawing. It's not that great because of the fact that I don't have a real pen for this. But yeah, so that's where our image would be. And clearly from the positions you can see on here, because the image is located behind the mirror or on the opposite side from the focal point and the object, you know that it's going to be a virtual image. Plus you can tell that by the fact that the rays that are completed to show where the image is are like imaginary rays in a sense, because the real rays are in the front of the mirror where the focal point and the object are. And because the image is above the central axis, you can tell that it is upright. It's in the same orientation as the object, and because it is larger than the object, you can tell it was magnified. So that just kind of backs up what we saw in our calculations here. It is magnified and the image is virtual. So I think that's all I have. Yeah, so thanks for watching.